What is the moment of a force? The moment of a force about an axis is the tendency of a force to produce rotation about an axis. Let's consider a wrench applied to a nut on a bolt. To obtain the maximum rotation or turning effect on the nut, force should be applied perpendicular to the handle, as far away from the axis through the center of the bolt as possible. The moment of a force about an axis is defined as the product of the force and the perpendicular distance from the line of action of the force to that axis. With forces in a plane, the moment of a force about a point is understood to mean the moment about an axis perpendicular to the plane at that point. Perpendicular distance from the line of action of F to point O is shown as BO. Let BO be equal to D. The moment of force F about O is equal to the product of F and D. The point O is the moment center, and the distance D is the arm of the force. A moment is also referred to as a torque. The two terms are sometimes used interchangeably. In U.S. customary units, moments or torques may be expressed in pound-foot, kip-foot, or pound-inch, and in the SI system, it's usually referred to in Newton-meters, kilonewton-meters, or Newton-millimeters. There are several details related to the moment of a force that we need to know before we solve any problem. First, the magnitude of a moment may be changed by varying either force F or perpendicular distance d. Second, the moment of a force about any point has a direction associated with it. If the direction is clockwise, it will be negative. If it's counterclockwise, it will be positive. Third, a given force can have different moments about different points. Different moments mean the magnitude, direction, or both. Last, if the line of action of a force passes through a point, then D equals 0, and the force has no moment about that point. What does the theorem of moment state? It states that the moment of a force about a point is equal to the sum of the moments of the components of that force about the same point. Let's look at resolving force F into x and y components. The component Fx has no moment about O because it acts directly through O. The sum of the components of the force are given by these equations. From the construction, we see that the moment of O equals Fy times r, so that Fy also equals F times sine theta. And if you walk your way back, you'll find that the Fy is just F sine theta and sine theta times d divided by sine theta. This still gets you back to the same points, so the result agrees with the definition of the moment of the force about O. Thus, the moment of the force F about O is equal to the sum of moments of the components of F about O. Let's look at this example. We need to find the moment of the 120-pound force at point C about points A, B, C, and D for the rigid body in figure A. If we take the moment around A, we set the moment always equal to the force times the letter r. The distance between A and C is 6 feet, so we would say that 120 pounds times 6 is 720 pounds-feet. It is the same thing for point B. The distance from C to B is 2 feet, so 120 times 2 equals 240 pounds-feet. These rotations are counterclockwise, so they will be positive. For the moment about C, the moment of the force about C will be 0 because the force acts directly through C and can have no moment about C because the distance is 0. As for D, if you take a moment around D, the moment is going to be clockwise, so it's going to be negative. It will be a negative 120 times 2 equals negative 240 pounds-feet. Let's look at another example. We need to determine the moment about C due to the force F of magnitude 100 newtons at point A to the bracket shown in Figure A. There are actually two methods to use when you have an inclined force like this. For solution 1, we construct the diagram shown in Figure B to determine the arm of the force D, that is the perpendicular distance from the force to the moment center at point C. From the right triangle ABE, we use the tangent of 30 degrees equals AB divided by BE, which equals 0.6 divided by BE. BE equals 0.6 divided by tangent 30 degrees, which equals 1.039 meters. From the right triangle CDE, we use the equation sine of 30 degrees equals D divided by CE, which equals D divided by 1.039 plus 0.8. D equals 1.839 sine of 30 degrees, which equals 0.9195 meters. So we find the total distance to be 0.9195 meters. Now we multiply the force times the arm of the force. Because the force is making a clockwise rotation from the convention, it will be negative. Negative 100 times 0.920 gives you negative 92.0 Newton meters. But if we look at the same problem and want to find the x and y components of the 100 Newton force, we use the theorem of the moment to find the moment around C. For solution 2, we find the Fx and the Fy. Fx equals 100 sine of 60 degrees equals 86.6 newtons. Fy equals 100 cosine of 60 degrees equals 50 newtons. Now we have two different forces, and we can find the moment for these separate forces, the Fx and the Fy. The Fx of 86 has a lever arm of 0.6 meters to point C, and the Fy has 0.8 meter force lever to point C. So the moment about C equals negative 50 times 0.8 minus 86.6 times 0.6, which equals negative 91.96 Newton meters, or 92 Newton meters.